When it comes to the pricing of financial derivatives, whether it be an option contract or some contract with a more complicated payout structure, it's hard to think of something more important than Ito's lemma in this space. And the reason for that is because the payout function of these contracts are driven by some sort of underlying asset. And typically that underlying asset, whether it be a stock or something else, is usually modeled as a stochastic differential equation. That is, the price path evolves randomly throughout time. In the context of a regular differential equation, we need the idea of a derivative. The big difference between a differential equation and a stochastic differential equation is we have to deal with this idea of randomness. In this video, I want to walk through Ito's lemma. I want to clearly explain the difference between the traditional derivative and this idea of Ito calculus. Going to do this graphically, going to do this as explicitly as possible. Hopefully by the end of the video, you'll understand why we go about deploying Ito's lemma to solve for this differential of a time-dependent function of a stochastic process. Let's start with this idea of the derivative from traditional calculus. So the derivative is defined in terms of a limit, and this limit definition can be used to prove all sorts of useful theorems, from the power rule to the product rule, so on and so forth. And typically when we first learn about the derivative, we learn about it in the context of instantaneous rate of change and the slope of a tangent line. So I've just gone about plotting the derivative of this very simple function, x squared, and at this point the derivative gives us the slope of the tangent line, the instantaneous rate of change. But the derivative is so much more than that in traditional calculus. We can solve all sorts of problems using it. We can solve differential equations, optimization problems, just to name a few. But this idea of a derivative starts to break down when we introduce the idea of randomness. And the reason for that is because when we have randomness, we're saying that there's some sort of random variable that follows a distribution with an expectation and a variance. If we make the same assumptions about the deterministic functions that we're operating on the stochastic functions that we're operating on, that is a function of a random variable, then things aren't going to add up. And we're going to see why in a moment. Before we talk about this idea of calculus with randomness, we need to understand a differential and a Taylor series expansion. A differential is very simply just a very small change. And critically, it's non-zero. It's a small change. Those are not the same thing. So what I've done is I've written explicitly out what this small change is. That is this dx term. That is the differential. And I'm saying that it's equal to x plus delta x minus x. So what happens if I plug in 0 for delta x? Well, we don't have a small change anymore. We just have 0, right? It's going to be x minus x. That is not the idea of a differential. We're saying as delta x approaches 0, it follows that dx is also going to approach 0. It represents an infinitely small change, but it's not precisely 0. Otherwise, mechanically, it wouldn't work as intended. So now that we acknowledge that dx is a differential, it represents an infinitely small change, we can move on to the Taylor series and better understand why it functions the way it does. Before we do that, I've plotted out this differential to show you this idea. That is, this delta x term, as it gets closer and closer to 0, we can see this blue line, that is this dx term, this differential, also approach 0. But very critically, this dx term will never actually be 0. Delta x is approaching 0. Moreover, dx is also approaching 0, representing a very, very small change that will never precisely be 0. Now that we understand the idea of a differential, we need to consider this Taylor series expansion. And the Taylor series expansion is going to confirm what we suggested earlier about the derivative, but it's very important to make the distinction between the linear approximation that is the derivative and the actual function's change at that particular point. What I mean by this is, let's take a look at this Taylor expansion here. We have f of x plus some small change is equal to f of x plus f prime of x times dx plus 1/2 second derivative of f of x times dx squared. Now, what I'm not saying is I'm not saying that these terms are negligible in the context of the change in function value at x plus dx. That is not what I'm saying at all. If you have to rewatch that portion of this video 10 times to understand it, please do. Because here we're saying that this precise change in the function is equal to this infinite series of function derivatives multiplied by some differential, maybe a higher order differential, and that is precisely true. But we're interested in the linear approximation, the slope of the tangent line given by the derivative. We're not interested in this precise change. We're interested in this first derivative. So what we can do is we can take this Taylor expansion and we can go ahead and plug it in to the definition of a derivative. And what you'll see here is if we plug in this Taylor series expansion into the definition of a derivative, we have this limit here, and it's the limit as dx approaches 0. And what you'll see very clearly is if we plug in this expansion, then f of x cancels out with f of x, and we're left with this limit as dx approaches 0. We can divide out the dx from this first order term, the second order term, and so on. And then we're just going to be left with the limit as dx approaches 0 of f prime of x plus 1/2 second derivative of f times this differential term, but we haven't applied the limit yet. So when we apply the limit, you'll see that we actually just end up with the derivative. So what's happening here? Well, this is confirming the idea that the higher order terms are going to become negligible as the dx, the differential, becomes arbitrarily small. That's exactly what we see here. We're saying, okay, if we have this Taylor expansion, we plug it into the definition of a derivative, you can see that the limit as the differential approaches 0, the higher order terms, that is this second derivative, third derivative, so on and so forth, will drop out because you just plug in 0 for this differential for taking this limit, and you end up with just the original derivative. So this is probably the most complicated component of this video, but this is confirming everything that we were trying to propose based on the idea of a differential. That is, in the context of the derivative, higher order differentials are going to drop out. They're going to become negligible in computing the precise first order derivative of this function f of x. And I've plotted it for you here to see. We're not trying to model the change in the function's value. If we were doing that, we would probably want a higher order representation, second, third, fourth order, to capture curvature and inflection and all of that good stuff. And you can see that in this green dotted line. The third order approximation hugs that green curve, the true change. But this red dotted line, remember, that is the derivative, the slope of the tangent line. That's the first order approximation given by this Taylor series when dx is very small, and it is approximating it very, very well, precisely, and that is because of this argument here. Long story short, if we apply the definition of a derivative to the Taylor series expansion, then we see that as the differential becomes arbitrarily small, the higher order terms are going to go to 0, and we're just going to be left with the derivative. And all the derivative is a linear approximation of change at a particular point. And because it's linear, you can see the further we get away from this original point, the worse we do, especially if the function has a lot of curvature. And that's why if you're trying to actually model the true change in the function, you probably need more terms. But remember, here we're only interested in the derivative because we're interested in solving all of the things that the derivative is used for solving. So we're interested in the differential equations, the optimization problems, and so on. So we're interested in the derivative here, not the true change in the function. And in this case, the function is deterministic. There is no randomness in the differential. So when we have a time-dependent function of a stochastic process, so think of a function of a random variable or a variable that evolves randomly over time, we have to consider the derivative in this case. It's actually quite different because if you look at this argument, what's going to happen is all of the higher order terms for that function and that derivative are not going to drop out. So very nicely here, if we just plug in 0, you can see that this higher order term drops out, the third derivative term will drop out, and so on and so forth. But when there is randomness, this is not the case, and we're going to see why. Now we're ready to deviate away from traditional calculus to this idea of stochastic calculus, and it'll be relatively intuitive coming from the Taylor series expansion of the derivative above. And that's because when we're looking at randomness over time, we have a small increment in the randomness and a small increment in time. Those are our differentials. And if we take a look at the differentials, we can see that in the same way that dx squared drops out in the first derivative, dt squared is going to drop out too as that differential becomes arbitrarily small. It's acting just like those higher order differentials above, just like we saw in this argument here with the limit. You could see these higher order terms are all going to continue to drop out when you evaluate that limit, and we're just going to be left with the derivative. The same is true here with the product of the differential of time and the differential of the Brownian motion. That is also going to go to 0 as the differential becomes arbitrarily small. But there's a big difference here. The big difference is when we take a look at the squared differential of Brownian motion. So these aren't too much of a surprise. This is exactly what we saw above with the Taylor series expansion for that first order derivative. But the big difference here is when we take a look at this term here, this differential of Brownian motion squared, this is actually going to go to dt. This is saying something about the quadratic variation, the variance of the Brownian motion. Now this is a big deal because all of the terms in the Taylor series expansion, those higher order terms, dropped out for our first derivative. But here, because this dwt squared term doesn't go to 0, that means this isn't going to drop out. So where does this come from? Why does this go to dt? Well, less formal, but more intuitively, we can understand that the increments in Brownian motion, that is, if we evaluate the Brownian motion at this point in time, and then we wait some delta t, maybe 1 day, and evaluate the Brownian motion at this point in time, then that increment is going to be a random variable. It'll be distributed normally with a mean 0 and a variance of that time step, that delta t, that change in time. And essentially all dwt is when this becomes arbitrarily small, when that increment becomes arbitrarily small. So as that delta t approaches 0, essentially we have that this differential here is going to be distributed normally with a mean 0 and a variance of dt, that infinitesimally small change in time. And if it wasn't the case, if this wasn't the case, and we had that dwt squared went to 0, then this would just be mean 0 with a variance of 0. We need to account for this quadratic variation that characterizes the Brownian motion increments. That is exactly why, and hopefully it's intuitively why, this dwt squared term can't go to 0. Otherwise, we wouldn't be accounting for this variation, this randomness, in the change over time. A pretty elegant way to see why this dwt squared term doesn't go to 0 is by taking a look at Brownian motion from 0 to some time cap t in the future. If we partition the space into cap n increments, then we have that w of t minus w of 0 is distributed normally with a mean 0 and a variance of delta t. The time step is just going to be to capital T in the future. So that means that this distribution is mean 0 with a variance of capital T. Now, if dwt squared was 0, like in the ordinary differentials in the context of the derivative, then it would follow that the variance here, given by this equation, would be simply 0. And that's because dwt squared, all of these dwt squareds would be 0, and the expectation is already 0 So the variance would be 0 plus 0, which is 0. But that's not going to be the variance that's demanded of this process over this interval, which is what? It's capital T. So that is more formally a way to see why dwt squared has to go to dt, because if we were to sum up all of those increments, that is those dt's, from 1 to cap n, we would end up with this desired distribution that characterizes the Brownian motion by construction. Using the idea of traditional calculus and the Taylor series expansion, we saw what happened to higher order differentials in the context of the derivative. They all dropped out. From stochastic calculus, we see that that's not necessarily the case. We saw that dwt squared term, that differential of the Brownian motion squared, go to dt. So what's the deal here? Well, we need to correct the interpretation from traditional calculus using a new interpretation from stochastic calculus, and that is precisely Ito's lemma. So what I've done here is I've defined a function that involves randomness. So remember, from traditional calculus, we have a function of a deterministic quantity. Here we have a function of a random quantity, that is this Brownian motion, and it's Brownian motion over time. So if we apply the Taylor expansion, then we're going to get this differential of the function is equivalent to this series of partial derivatives scaled by their respective differentials. But we know how to handle these differentials now from the original Taylor series in traditional calculus, along with our rules from stochastic calculus. So what can we say about this equation? Well, as dt squared goes to 0, we can simplify this expansion and just say that this term involving dt squared goes to 0. Because remember, we're after the derivative. Okay, what about the differential of Brownian motion squared? Well, here it's going to approach dt, so we can substitute in dt for dwt squared. Moreover, the product of dt and dwt is going to approach 0. Leaving this cross term here to be 0. So after simplifying, we can go ahead and then factor out the dt, and we are left with this. This is going to be the solution given by Ito's lemma. The differential of a time-dependent function of a Brownian motion will be given by this quantity. And this is applying the idea from the Taylor series expansion in traditional calculus and how to deal with the differentials in tandem with the stochastic calculus rules that allow us to drop out these higher order terms and transform this differential of Brownian motion squared into that quadratic variation accounted for by dt. Now, everything we've discussed up until this point is showing precisely with the mathematics what is going on, but I think a simulation to illustrate this idea makes it a little more tangible. So what I have here is I have a sample path of Brownian motion. I've zoomed in and I've looked at the differential given by Ito's lemma and the Taylor series. So that's from traditional calculus. And I've also looked at the actual differential given by this Brownian motion path. And what you'll see is Ito's lemma and the Taylor series differential, they're not precisely equivalent. There's some space between the two, otherwise they would be perfectly overlaid, but they don't line up with this actual differential. Why is that not the case? Well, remember, we're dealing with randomness. Whenever we're dealing with randomness, we're not looking at predicting a path. We're not looking at predicting an increment. We're looking at characterizing the distribution, that is the expectation and the variance associated with that randomness. So this is just one sample path of the Brownian motion. So why is Ito's lemma and the Taylor series useful at all if it's not lining up with the actual differential? Well, the reason why it's useful is because if we do this for a series of sample paths and then take the average differential, then we are going to match Ito's lemma. And I've done that below in this chart. What I've done is I've compared the differential for over 1,000 simulations of the Brownian motion, and you can see that the red line is the average actual differential, and the green dotted line that tracks it almost perfectly is Ito's lemma is the Ito's lemma differential. But take a look at the Taylor differential with no correction term from that Brownian motion, that differential of Brownian motion squared being dt. You can see that it is nowhere near the correct value, and that is the source of the Ito correction term. We need to shift that up, and that's precisely what Ito's lemma does. Now, why doesn't this perfectly match the actual average differential? That is because this is, by the law of large numbers, going to converge as we iteratively sample from the same distribution, but this is precisely what Ito's lemma is doing. Ito's lemma is going to tell us how the process, the differential of that time-dependent function of a stochastic process, in this case just the Brownian motion, is going to behave when you take a look at the average differential. So the average difference of all of these Brownian motion paths, and that's what we're seeing in this chart. That's going to do it for this video on Ito's lemma. I hope you enjoyed. We're now ready to tackle more complicated topics involving stochastic differential equations. If you'd like to see some more videos on those topics, please leave a comment below, like, subscribe, check out quantguild.com, follow us on all of our socials. Other than that, thank you so much for watching, and I will see you in the next video.